Synthesis of nickel-rich doped lithium-nickel cobalt oxide, aluminium and iron dopant cathode materials, and their electrochemical performance.
Private cars, motorcycles, light and heavy vehicles all play a significant role in Malaysia's declining air quality. Therefore, more green transportation projects should be implemented, such as electric vehicles, to increase eco-friendly electric vehicles and decrease fossil fuel vehicles on Malaysian roads, and reach Paris Agreement zero carbon engine. Cobalt is an essential element in LiPs and already in a short supply today. The prices are expensive and have become the main reason behind the high cost of EVs. One way to reduce the cost of EVs is by reducing the price of LiP, and this can be achieved by minimizing the use of cobalt in LiPs. The modified nickel-rich lithium-nickel cobalt aluminum oxide and lithium-nickel cobalt iron oxide with excellent structural stability will give a good electrochemical performance, and this will make the dream to realize nickel-rich lithium-nickel cobalt aluminum oxide and lithium-nickel cobalt iron oxide into the market become closer. The objective of this study is first to determine the purity of synthesized nickel-rich nickel cobalt aluminum oxide and lithium nickel cobalt iron oxide cathode materials using X-ray diffraction (XRD). Second is to determine the morphology and crystal dimension of synthesized cathode materials using a field emission scanning electron microscope (FESM) and energy dispersive X-ray spectroscopy (EDX). Since the 1970s, lithium-ion batteries have been researched. Sony Corporation commercialized the first lithium-ion battery in the world in 1991. After that, they were used in a wide range of applications including video cameras, cell phones, drones, and electric cars. The adoption of electric vehicles could increase in the future if lithium-ion batteries' performance continue to grow and new modes of transportation like electric aviation could become a reality. Components of LiPs, which comprise of anode cathode separator, electrolyte, and two current collectors that make up a battery, positive and negative. The electrolyte is a liquid composed of lithium salt dissolved in organic solvent with graphite serving as the anode and transition metal oxide as the cathode. Among the LiPs components, the cathode is the key materials for energy capacity. The lithium cobalt oxide and lithium iron phosphate are typical cathode materials for consumer electronics and small rechargeable batteries. The energy density and structural stability that can be achieved in this class of materials have significantly improved because of the combining of transition metals to create nickel-rich layer oxide. A higher nickel content because of its high electrochemical redox activity is generally thought to increase energy density. Cobalt, on the other hand, is good for red capability and crucial during synthesis to create well-ordered layer structure. Lithium nickel mangan cobalt oxide doped with aluminium and iron was effectively synthesized by Elias Radwich using the co-precipitation method. It has been reported that the replacement of an electrochemically active element with an electrochemically inert element such as aluminium might result in a capacity loss. Contrarily, the iron doping does not offer any increased capacity over the electrochemically inert aluminium as well. When iron is added, the lithium diffusion is hindered more and oxidation potential of the nickel ion is increased by the iron ion, which is the main cause of decreased discharge capacity in nickel-rich materials. The co-precipitation method is used to make aluminium and iron doped nickel-rich lithium-nickel cobalt oxide layer cathode materials. The mass of starting material, which is nickel 2 sulfate, cobalt 2 sulfate, and aluminium 3 nitrate, are dissolved in the aluminous water at room temperature. After that, the mixture is added with sodium hydroxide and stirred to obtain a homogeneous solution. Two mixtures are mixed at the same time. A homogeneous solution is added every 10 minutes until pH 11 is obtained. The solution is heated at 55 to 60 degrees Celsius. After that, the precipitate is filtered, then washed several times. Then the precipitate is dried off at night. Precursor is sintered at 480 degrees Celsius for 5 hours, and the precursor is grounded using agate mortar to get fine powders. At this stage, we use two different lithium sources, which are lithium hydroxide and lithium carbonate, to mix with nickel cobalt hydroxide precursor. Fine powders undergo sanding process at 920 degrees Celsius for 15 hours. The figure shows the result of XRD of nickel-rich lithium nickel cobalt aluminum oxide, where B and C is using lithium carbonate as a lithium source. The ratio of nickel cobalt aluminum hydroxide precursor to lithium carbonate in B is 1 to 1.55. Then, since the result of B is not pure, we increase the amount of lithium carbonate in C with ratio of nickel cobalt aluminum hydroxide precursor to lithium carbonate is 1 to 3.055. The result in D shows the XRD result of nickel-rich lithium nickel cobalt aluminum oxide using lithium hydroxide as a lithium source. It was revealed that the synthesis sample C1 and C12 were not pure and multi-phase. Meanwhile, the synthesis sample C13 is pure and single-phase, which has hexagonal layer alpha sodium iron oxide structure crystallizing. This result shows that using lithium hydroxide is more easier to achieve pure and single phase of nickel-rich cathode materials, which has similar crystal structure to lithium cobalt oxide, as compared using better than lithium carbonate as a lithium source. The table shows the result of calculated reference intensity ratio (RIR) of nickel-rich lithium nickel cobalt aluminum oxide and lithium nickel cobalt iron oxide, which are 0.7219 and 0.7131 respectively. It was shown that C13 has higher IRI compared to C2. It can conclude that 1% aluminium is better dopant than 1% iron dopant. But why? Because higher intensity indicates high crystallinity. However, 104 peaks intensity is higher than 003 peaks. This indicates that even though this material is pure, but it still has a common problem in nickel-rich cathode material, which has higher cation mixing. The result shows the comparison of RIR between 500 rpm and 1000 rpm of lithium nickel cobalt aluminum oxide. According to LiNi0.89Co0.1M0.1O2, RIR value higher than 1.2. It is reported that the crystal structure will have low cation mixing, which gives a good cation ordering, which later yield a good electrochemical property. It is discovered that 1% aluminum doped lithium nickel cobalt oxide, when it is stirred under 1000 rpm, shows high IR compared to 500 rpm. So 1000 rpm is the best stirring speed. These are VSM images that were taken at magnification of 1000 times, 5000 times, and 20,000 times for sample C13, and the results are shown in the figure. The sample have a very crystalline structure and similar type of morphology, which is irregular shape, and nothing much changes can be seen after aluminium dope in nickel-rich lithium nickel cobalt oxide. The scanning, electron microscopy, and energy-dispersive X-ray spectroscopy had been used on 1% aluminium-doped lithium-nickel cobalt oxide C14 sample to determine elemental composition of the material. The area image of study, spectrum, and elemental data for 1% aluminium-doped lithium-nickel cobalt oxide C14 sample are shown in the figure. The results show that cobalt content are lower than theoretically calculated, which is supposedly 10%. Whereas aluminium content is slightly higher than the expected, which is supposedly 1% from the total atomic. Meanwhile, nickel content shows the expected result, which is 89%. The mapping analysis were done for 1% aluminium doped lithium nickel cobalt oxide C14 sample to see the elemental distribution throughout the sample, and the spectra are shown in the figure. From the mapping analysis, it can be concluded that the elements are well distributed. In conclusion, dopant including aluminum and iron were used which the doping level were set up by at 1% and based on the result then both showed the positive result and had the potential of reducing the cation mixing that are by having nickel-rich lithium-nickel cobalt oxide cathode materials. Overall, these dopants were successfully synthesized via co-precipitation method with the usage of high RPM of homogenizer at 1000 RPM. For future study, battery testing must be conducted to observe the capacity, cyclability, and the battery's lifetime.